So we are going to do the revision on equilibrium. Okay, so the revision under equilibrium, you need to understand that any equilibrium, it involves these reversible reactions. Okay, like for example, if I have A plus B to give me C plus D, okay, you need to have that reversible sign over there. And this reaction, okay, we say as, okay, if you say dynamic equilibrium or something like that, we have, okay, the situation must be they are dynamic. What is the meaning of dynamic? They are always going to happen. It means they are always reacting, they are not stopping. And then the rate of forward reaction is the same as the rate of reverse reaction. So this is also telling you that, okay, the reaction is dynamic, but there is nothing like the forward rate is faster, okay, the backward rate is faster. No, the rate is going to be the same. And because of the rate is going to be the same, the concentration of all the reactant and the products, they remain constant. Now, this constant doesn't mean that they are equal. Okay, students always think that they are equal, or this is 0.01. Okay, and this must be 0.01. No, not really. Okay, it means constant means they don't change. Okay, so all, okay, the concentration of reactant and the concentration of product, they remain constant, a fixed value. And there is going to be a closed system. Okay, what is closed system? Nothing goes in and nothing goes out. You are not removing any of the product out. You are not adding anything in. That is the meaning of closed system. Okay, so sometimes we do have open system where we remove something. Okay, when we remove something, so of course when we add and remove something, okay, there is a need to re-establish the equilibrium. Yeah, so during that time, okay, when you are re-establishing the equilibrium, then when they became or establishing a new equilibrium, that is the point where the system is going to be closed. So it doesn't mean that, okay, equilibrium, we cannot add anything inside. We cannot remove anything outside. You just need to remember the moment that they reach equilibrium, it is in the closed system. But when you remove or you add, it's already open. So there is a need to recalibrate the system. Okay, it means the system will reach the equilibrium, a new equilibrium again. Once they reach the new equilibrium, when they are dynamic, forward reaction rate and backward reaction rate is the same rate, concentration remains constant, then you are already having a new equilibrium. Yeah, that is going to be the characteristic. So we are going to also learn about, okay, this Le-Chatelier's principle. Okay, this Le-Chatelier's principle is stating that, okay, you can see the definition basically in a simple term. Whenever you make changes in equilibrium, when you make changes in a system that already reached equilibrium, what happens? Okay, the system itself will oppose the change. Okay, like when you add something, they will try to remove that. Okay, when you remove something, they try to compensate that by forming more. Okay, so that is going to be Le-Chatelier's principle. And in fact, in your textbook, they have given this example, stalactite and stalagmites. And they say that, okay, this is going to be the equation. Okay, let's say they ask you similar question in exam. I think it is also important to understand how the formation of these stalactites and stalagmites are going to be there. Okay, the reason is, okay, in order to form this is going to be your limestone. Okay, limestone together with water, together with the carbon dioxide that is trapped within the carbon dioxide and the water, okay, they will form this compound. Okay, so what happens? Okay, carbon dioxide, they don't remain trapped. Okay, what happens? Some of them, they go out. Okay, this is the part that I said that, okay, if it is in a closed system, it's okay. But in this case, they are moving out. Okay, so there is a disruption that is happening in the system. So what happens over here, the moment the carbon dioxide is going out, the system now have to compensate. The carbon dioxide is reduced. So you need to form more carbon dioxide. If you want to form more, yeah, of course, you need to put the arrow towards to your left. You want to form more carbon dioxide. Okay, so this will react to give you or decompose to give you this. Okay, so during that process, what happens? You are going to have more calcium carbonate being formed. And this calcium carbonate is the one that is responsible for all these formations, stalactites and stalagmites. Okay, so if they ask you to explain this, yeah, you already have an idea. Yeah, so if you read through the textbook, yeah, now you can understand better. Okay, but now if you look at the checkpoint, okay, you see here, explain what happens to the position of the equilibrium if you are adding more of this. Okay, so if you are adding more of this, okay, according to LCP, I'm going to use LCP for large Chatelain's principle. Okay, so when I have more, I need to reduce it. How do I reduce it? By reacting them. So move to the left. Okay, so the position of the equilibrium will move to the left, okay, to form more reactants. Okay, and if you have a situation where you are going to remove, okay, this particular alcohol, ethanol over here, so you are reducing that ethanol. Okay, so LCP is going to try to increase that concentration of ethanol. So they will try to form more ethanol. Okay, they will form more ethanol. So the reaction will go backwards. So towards to form more reactant. Okay, therefore the position of the equilibrium will be shifted to the left. Okay, so you can check, okay, how do you explain and so on, but the answers are all there. Okay, but if you have this situation over here, they say explain what happens to the position of the equilibrium when Fe2 plus is increased. Fe2 plus increase, you want to decrease them, so you move to the right. If water is added to the equilibrium mixture, you see all of them are aqueous. So what water will do? Water will dilute everything. Okay, they will dilute everything. So nothing will happen, no change. Okay, there is no change in position of the equilibrium. But some of you will be asking, is it going to be applicable for all situations? The answer is no. If you look at this example, okay, the first example, you can see water is being involved in the reaction as, okay, in this case, as part of the product. Now, if they are involved as a product, not as a solvent, okay, you need to include them in your Caei expression. Okay, you need to include, later we will learn about Caei. You need to include them because they are part of the product. Okay, they are part of the reactant and product. So you need to include them. So if let's say I'm adding water, for example, okay, I am adding water means I'm increasing the concentration of water. Okay, so what you need to do, the position will shift to the left to remove that water. Okay, to reduce the concentration of water. Okay, so this one is going to be something extra, yeah, because most of the question, I think students will get confused with water. Okay, so I have already explained about water. It depends, okay, whether the water is going to be as a solvent or whether they are reactant or product. If they are reactant or product, they must be involved in the Caei expression. Yeah, very important. Now next, okay, first I have covered about concentration. Okay, I put concentration. Second is going to be about pressure, but I think whenever we talk about pressure and so on, I think how to apply and everything, students, they kind of understand how to apply. But I think some of the students, they still confused, why less number of molecules, why more number of molecules and so on. I think to understand that, you need to also see here. Like for example, if you have 5 particles over here, okay, so if you have 5 particles, if you have more pressure, it means there's going to be more concentration. You press them, okay, they are going to be occupying a smaller volume. Yeah, if it is lower pressure, they have bigger volume, lower concentration. So that is how they are related to concentration. Okay, but okay, if you just want to look at it in form of number of moles or number of molecules, you can see this example. This example, they say this is purple is going to be X, Y is going to be green, and you can see this one is going to be Z. Okay, they say it's one in the beginning, yeah, there is going to be one molecule of Z. Okay, but they say that if you increase the pressure, what will happen? Yeah, according to this equation, according to what we have learned, okay, we count the number of molecules. Like for example, 1 mole, so we say 2 moles, and this is going to be 1. When I increase the pressure, I need to counter-react the change. It means I need to decrease the pressure. How do I decrease the pressure? I want to make the number of moles to be less. I don't want it to be too many molecules over there. So how do I decrease them? Very simple. Join them. Get them married to each other. Okay. Now you have 13 molecules. You join. Now you have only 12 molecules now. Okay, you join them together, so you have 11 molecules. So what is happening over here? You are forming products, and that product is going to be counted as 1. Earlier they were counted as 2. So that is the meaning. Okay, when you say pressure is increased, what does it mean? Okay, they are telling us that when pressure is increasing, I need to decrease the pressure. How? Okay, this to move towards the less number of molecules is going to be one of the way, okay, to form more products, okay, where you can have the pressure to be reduced back again. Yeah, this is going to explain based on diagram. Okay, please go through this diagram again, or please go through this video again if you don't understand. But now, whatever it is, okay, I think you still need to understand how to apply them. Yeah, again, look at when we are talking about pressure, it means it must be gas. So you look at the number of moles, 2 moles, 2 and 1, total 3. Okay, so when you increase pressure, what will happen? When you decrease the pressure, what will happen? So I will use the red pen over here. According to LCP, you need to decrease them back. Okay, you need to decrease the pressure. How do you decrease the pressure? By shifting the position of the equilibrium towards lower number of molecules. Okay, so they are going to move to the right with lower number of molecules. Okay, lower number of molecules. I'll just put down over there. Okay, so this is going to be what is going to happen. Shifted to the right towards lower number of molecules. Okay, and what will happen if I'm using, okay, for example, I'm using lower pressure. Okay, so if you have lower pressure, I need to increase the pressure back again. So how do I increase the pressure from 2 to become 3? I need to go towards the larger number of molecules. Okay, so I will try to, according to LCP, I need to move to the left, okay, towards, okay, to higher number of molecules. Okay, that is what is happening over there. Okay, so when you explain, okay, if you look at the way that we explain for concentration, we just say the position is shifted to the left or shifted to the right, depends to form more product or to form more reactant. That is how you explain. But for pressure, rather than saying shifted to the right, to the left alone, you include another one more point. They are shifted to the right, towards lower number of molecules, okay, or towards less number of particles. You mentioned that, okay. They are going to be shifted to the left to higher number of molecules and so on. Yeah, so please refer to that. Okay, so if you have this situation, like there are some other examples, two more examples, which is the same. I will just go through this nitrogen plus 3 hydrogen, okay, to give you 2 ammonia. Okay, all of them are going to be gas. Okay, very important. It must be dealing with gas. So you see 4, total 4, 1 and 3, and then 2. So if you increase the pressure, okay, if you increase the pressure, according to LCP, you need to decrease the pressure. So the position of the equilibrium will be moved towards to the right to favor less number of molecules. Okay, so even in this explanation, they don't explain. They say it will favor products. Okay, but in your exam, you must mention this. Okay, I'm telling you because, okay, in your exam, if you don't mention this, you will not get the mark. Okay, very, very important. Yeah. So the same thing, when pressure decrease, you can just put over there. Okay, you can go through on your own. Okay, so let's actually try some questions over here. Now, here, okay, you see both of them are gas, no problem. So 2 and 1. We are going to predict the effect of increasing pressure. So increase pressure, you need to decrease the pressure. So you need to go to the left. So when you explain it will shift to the left towards fewer gas molecule on the left. So that is the reason I'm actually asking you to include that number of particles. It is very important. The second part, you see here solid and solid. One of the common mistake is treating pressure as the same throughout. Wrong. When you are talking about pressure, we are talking about gas only. So you focus only on the gas. So it's only 1, 0 here, nothing. So 0. So if you increase the pressure, you need to decrease the pressure. So it will move from 1 to 0. Yeah. So the position is going to be moving to the left and then same explanation. Yeah. So you need to remember this. Now, what if we have some kind of a different type of question? Predict the effect, okay, of decreasing pressure on this reaction. Yeah, I think this one not so different. This is simple. This is 3 and 2. If you decrease the pressure, you need to increase the pressure. Yeah, you are going to have more NO, you are going to get more oxygen. So it means the decomposition is going to be more. Okay, and also remember NO2 is a brown gas. So maybe if they ask you the observation, okay, the brown color will become slightly colorless or faded. You can mention all this. Yeah, so that is going to be about, okay, pressure. So if I recall again, I have went through concentration. Number 2, we went through pressure. Now we go into number 3, which is going to be the temperature. Okay, for temperature, okay, I will just straight away use my method. Maybe this one, the other students are already aware about this. So maybe Jackson, maybe you try to adjust to my method a bit. Okay, my method is basically like this. Okay, so if I have 2HI, okay, and then I have H2 and I2. And if I have this 2SO2 plus O2, and this is going to be 2SO3, and this one is going to be endothermic reaction. This is going to be exothermic reaction. Yeah. Now, so my method is basically quite simple. If it is endothermic, okay, endothermic means heat is being absorbed from the surrounding. So if I put my hand over there, my hand is a surrounding. So my hand will feel cold. Okay, over here. So if I put another hand over here, okay, my hand will feel hot over here. Yeah. So what happens over here, if I increase the temperature, according to LCP, I need to decrease the temperature. How do I decrease the temperature? By moving, okay, by moving from hot to cold. Okay, that is how you decrease the temperature. Hot to become cold. Yeah. So my position of the equilibrium is shifted to the right. Okay, but you do not explain like that in your exam. Never explain the position is moving to the right and full stop. Wrong. Yeah, you need to include more details. Okay, you can say that the position is shifted to the right if you want. Yeah, to the right. Okay, favoring. Okay, favoring. So you see, if it is going to the right, this is going to be endothermic reaction, favoring endothermic reaction. Okay, so you need to mention whether they will favor endothermic or whether they are going to favor exothermic. Like for example, if you decrease the temperature, what will happen? I need to increase the temperature. How do I increase the temperature? Of course, from cold to become hot. So when cold to become hot, I know this is positive. So if you're moving backwards, then it's going to be exothermic. So you can say it is going to be shifted to the left if you want. Okay, but more important is favoring exothermic reaction. This is very, very important. So now, okay, using what I have taught you, maybe now Jackson can actually understand slightly better. I will actually try to do it again. Okay, you see, if you have, this is going to be exothermic. Exothermic means heat is released to the surrounding. So if I put my hand over there, I will feel hot. Okay, to the right. Okay, if I put my hand over here, I will feel cold. Okay, so if let's say I increase the temperature, according to LCP, I need to decrease the temperature. How do I decrease the temperature? By hot changing to cold. Okay, so I am shifting the position of the equilibrium towards my left, but in your exam, you don't mention that way. You say it is going to favor or favoring, it will actually shifted to the left, favoring, this is exo. If it is going behind, then favoring endothermic reaction. I hope you understand this. Yeah. So if I have situation, let's say temperature is decreased according to LCP, I need to increase the temperature. How do I increase the temperature from cold to become hot? Okay. The position is shifted to the right, favoring, okay, favoring what? Favoring, this is negative, exothermic reaction. Okay, so you mention this. Make sure you mention this. Very, very important. Yeah. So that is about temperature. Okay, I have actually went through all this. So this one I left empty space over here to go through everything, but I have done this over here. Yeah. And then if you look at the checkpoint over here, they say that, okay, predict the effect of increasing temperature on the following reaction. Okay, you see this is positive. Yeah. So if I put my hand over here, the forward reaction, this is going to be positive. Heat is absorbed, so it's going to be cold. And this is going to be hot. Okay, so if I increase the temperature, it means that I need to decrease the temperature. How do I decrease the temperature? By moving hot to become cold. Position is shifted to the right. Okay, and when I'm shifting it to the right, it means it's favoring endothermic reaction. Favor endothermic reaction. So this is what you should write in your exam. Yeah. So here you see, okay, it is going to be shifted to the right. Endothermic reaction is favored. Okay. In this following reaction, sometimes they have this kind of reaction which is slightly different. Yeah. They say that increasing temperature increases the amount of carbon dioxide at constant pressure. Is this exothermic or endothermic? How I like to do this? Okay, I will use trial and error. Okay, I will assume that this is delta H. I will say, okay, let's say I'm going to try that this is going to be exothermic. Okay, so imagine this is exothermic. What will happen? If I put my hand over here, this is going to be hot. This is going to be cold. If I increase the temperature increase, I need to decrease the temperature. So how do I decrease the temperature? By hot going towards cold. Okay, and they mentioned more carbon dioxide is being formed. If I follow this, it means I'm going to reduce my number of carbon dioxide. Therefore, I have confirmed that this is wrong. So if this is wrong, what is our prediction? This is endothermic. Okay, this is endothermic. Why? If they ask you why, if this is positive, yeah, I know this is cold and I know this is hot, increase the temperature, you need to move towards cold. So you just say, okay, when you increase the temperature, okay, the forward reaction is favored, okay, favoring production of carbon dioxide, okay, which is favoring exothermic reaction. Yeah, so you just try to adjust all the sentence over there. But I taught you how do you do this question. It means you do trial and error. In the end, it's just two options, okay, whether endo or exo, you try. Yeah, so I recall again, we have done, okay, concentration, we have done pressure, we have done temperature. Now, okay, we come into catalyst. Now, if you look at all this, okay, these are the factors that might affect rate of reaction. If you increase concentration, yeah, rate will increase. If you increase pressure, rate will increase. Increase temperature, rate will increase. If you put catalyst, rate also will increase. Okay, but very important when it comes to catalyst, do remember rate of forward reaction and rate of backward reaction are increased. Not only one, yeah, forward and backward. Okay, so it means that if we are asking you, is there any change towards when you add catalyst towards position of the equilibrium? The answer is no. Okay, only these three will affect the position of the equilibrium. Catalysts do not affect position of the equilibrium. Why? Because they increase both forward and backward rate. So there won't be any problem when it comes to position of the equilibrium. Yeah. So that is going to be about catalyst. Done. Yeah. So the next part is going to be talking about equilibrium constant. How do we represent equation? So imagine if you have this equation and then you can write the equation this way. It's going to be product. You can see product and then P and Q to the power, okay, and divided by the reactant. If this one is quite difficult for you to see, okay, you can always straight away use an example over here, okay, where you can see the ammonia, okay, concentration of ammonia to the power of 2, okay, concentration of hydrogen to the power of 3. Concentration of nitrogen to the power of 1. No need to write down. Yeah. So this one, it means times. Okay. Times. So they don't show over there. Yeah. It is times. Okay. That is the expression. Take note, Kc can be used for both gas. Okay. It can be also used for liquid. Okay. It is also going to be used for aqueous. Okay. You can use them. Yeah. For Kc. Okay, but especially just only for gas, then we use Kp. Later we will learn about Kp. Yeah, so this is Kp. The same thing applies to the Kc over here. Similar, okay, SO3. Okay, you put SO3 at the top to the power of 2. Okay, SO2 to the power of 2, O2. Same. Okay, so what is very important over here? There is only one part very important over here. Your Kp and Kc are only affected, okay, are only affected by temperature. So it means if you have any change, okay, in terms of, let's say, for example, if you have any change in terms of temperature, if you have any changes in terms of concentration, okay, any changes in terms of concentration, in terms of pressure, and you add catalyst, they will not affect your Kp and Kc. Your Kc is only affected by temperature. Please remember this. Yeah. So when it's pressure change, concentration change, or you put catalyst, they are not affected. They are going to remain constant. Yeah. So checkpoint number 4. Okay. You see, this is going to be some examples I put over there. If I want to write down the Kc for this, how do I write? Okay. First of all, we will not include solid because solid will give you a constant concentration. We will not include solid. So it's going to be concentration of Fe3 plus, okay, put the bracket. Okay, this is going to be the product divided by Ag plus, okay, to the power of 1, Fe2 plus, close like that. Okay, and do remember, if they ask you to find out what is going to be the unit, quite simple. Concentration is mole per dm cube. And this one, mole per dm cube times mole per dm cube is mole per dm cube. If you want to write it twice also can. Okay. And then you cancel is 1 per mole per dm cube. If you bring it up, it's mole negative 1 dm to the power of 3. Sir, this is so easy. Do they ask in the exam? The answer is yes. Okay, this is one of the simple questions that they have asked before. They ask you to find the expression of Kc for this equation. Very simple. You see, ammonia to the power of 2, ammonia to the power of 2 to the power of 2. This is wrong. This is wrong. Divided by nitrogen and hydrogen, hydrogen to the power of 3. Hydrogen must be to the power of 3, hydrogen to the power of 3. The only thing that is going to be they are testing is plus or times. Of course, the answer is going to be times, not plus. Okay, you need to know about that. Okay, so maybe for now you might think it's okay. Why so easy? But when you study everything, when they ask you, you will make this kind of mistakes. Okay, so the next question is, okay, this is going to be involving a little bit of calculation. Okay, what kind of calculation? This one is very important as well. If you have CH3CO CH3, okay, plus HCN, and then if I have this CH3COH, I'll just rewrite again. What you need to do involving this, you use this ICE method. What is ICE method? Initial, change, and equilibrium. Initial, change, and equilibrium. Initially, according to the question, initially you have 0.05 mole per dm cube. So just assume that we are going to use 1 dm cube over here. So I just put moles, 0.05. And then you have 0.05 of ACN over there. Initially, okay, it means if they are adding two reactant, there should not be any product, zero. Yeah, zero. And then they leave it for a while to reach the equilibrium. They say the equilibrium of the product, they say that this is the equilibrium. So 0.0233. So what does it mean? From zero to become this, it means there is an increase of 0.0233. Okay, that is very important. There is an increase. You remember here number of moles, 1 mole, okay, to give you 1 mole. If there is a change over here, okay, that is represented by 1 mole. Of course, it's going to be, the change will be the same over here. But you need to remember, this is going to be reactant. Just now, that is going to be product. Product, you plus. Reactant must be reacting what? So, must be minus. So what you need to do is to find out what is going to be the value of that. Okay, the value of that, if you calculate the value, okay, if you have your calculator, you can calculate now. Okay, the value is going to be, I'll just calculate quickly, 0.05, okay, minus 0.0233. Okay, so I have 0.0267. 0.0267. So when I have this information, okay, so when I write down, okay, what is going to be my Caei, I don't want to write the expression. I know that this divided by this, okay, and then all to the power of 1. I'll skip that part. I'll just put 0.0233 divided by 1. Normally, I like to put divided by 1 because it is reminding me that this is going to be concentration, not number of moles. Yeah, 1 is 1 dm cube. So divided by, okay, divided by 0.0267 divided by 1, and then 0.0267 divided by 1. Okay, if you do that, okay, if you calculate, okay, it's going to be 0.0233, okay, and then divided by, okay, if I put a bracket, 0.0267 times 0.0267. Okay, if I close the bracket, I supposed to get 32.7. Okay, and then if I'm looking into the unit, okay, you can see this one, mole per dm cube divided by mole per dm cube to the power of 2. Okay, so that will be cancelled with this. So 1 per mole per dm cube. So it will be mole negative 1 dm to the power of 3. So if that's the reason why, if you look over here, they have given the answer like this. Okay, that will be the answer. So you can calculate that. Yeah. So of course, I don't want to waste the same time, our precious time to go through this. It's still the same method. You use the same method, ICE method. You should be able to calculate this. Okay, but please take note. Okay, not everything in your textbook is 100% correct. Yeah. Okay, there is a typo error. You just when you calculate, please check. Okay, when you have this, okay, this value, if you compare with this value that they have used, they are different. Okay, so you just double check. Maybe the answer is going to be wrong. Okay, so maybe typo will be here. Okay, it should be 0.0645. Yeah, so there is a typo error. Yeah, but the way how to do is still going to be the same. Yeah, now next question. Yeah, as I told you, please check. Okay, when now you revise, you can see a lot of mistakes in the book. Okay, you can see one of the mistake also in the textbook is this one. Okay, you can see there is an error. Can you identify this? Maybe I'll ask Megan. Megan, can you identify the error in the equation over there?
The oxygen is not balanced.
Yeah, so it's actually, if you look at it, is NO2 plus O2 suddenly become NO. It doesn't make sense. Okay, it's supposed to be NO. Okay, it's supposed to be this one, NO plus O2 to give you NO2. Then it makes sense. Okay, so if you put it over here, yeah, because just now the oxygen is not balanced because of that. So Now it should be balanced now, yeah. But you check later, this is going to be NO2, so that's going to be 4 oxygen to the left. So now it's all balanced. Okay, now deduce the effect of increasing temperature on Kc. Do remember Kc. So if you increase the temperature, what will happen? Now you can write down the full expression of Kc, okay, but I will just write down it's supposed to be product divided by reactant. Yeah, if I just put it as a simple way. So if I have this being negative, so this one I put my hand, this is going to be hot. If I increase temperature, I need to decrease the temperature. How do I decrease the temperature? From hot to become cold. So I am going to move to the left. If I'm moving to the left, I'm increasing the reactant. So reactant is going to be increased. So when product divide by higher amount of reactant, the value of reactant is more. Of course, I can say the Kc is going to be decreasing. Okay, so that is the effect. Okay, you can see the Kc is decreasing. So I'll just teach you how to get it done very fast. Okay, explain why increasing concentration of oxygen does not affect the value of Kc. Okay, rather than saying that okay, Kc is only affected by temperature, you need to explain properly. Yeah, why concentration? So when you increase the concentration of oxygen, what happens? Okay, according to LCP, you need to decrease the concentration of oxygen. So during that part, the position of the equilibrium will be moving to the right. So NO2 is increased and oxygen is decreased. So you just see NO2 is increasing, this one is decreasing. So this value will readjust itself so that you go back to the original Kc. Okay, so it will be constant. That's the explanation. Yeah, so this one please read again. Yeah, please read again why. Yeah, how to explain rather than simply explaining Kc is only affected by temperature. That is very weak. Yeah, you are already JC students. You need to explain further. Yeah, so next, okay, is going to be related to partial pressure. Okay, so if you look at this partial pressure, why we are learning? Because just now I mentioned about Kc and then Kp. Now we are talking about Kp. It means if you have an equilibrium and they are all in gaseous form. For example, you see this Haber process. All of them are in gaseous form. So I can actually write them, instead of writing them as Kc, I can write them as Kp. And you see how it is written. P to the power of 2. Okay, some of them actually write P NH3 and then to the power of 2. Depends. I'll just leave it to you. Okay, but this is how they write it in the textbook. Okay, you can write it. Okay, whatever way that you write, okay, make sure you get the final answer correct. That is my point over here. Yeah, so no point you write everything correctly, but in the answer you are getting it wrong. Yeah, so make sure you get the final answer correct. So you see the same. Yeah, so to the power of 3 over here, same. Yeah, product divided by reactant. But to understand better about this partial pressure, you need to look at this diagram. Like for example, in a container, if you have a total pressure 11 Pascal, for example, that is contributed by molecule A and contributed by B, for example. You add them together, then it's 11 Pascal. If I separate the molecule A, I separate molecule B, and I found out, okay, this one is going to give me 3, and this is going to give me 8. Because why? More molecules, you will have higher pressure. Okay, the ability to hit the wall of the container will be more. So what happens? There's only A and B inside that container, and the pressure must be coming from A and B alone. So what happens? The total pressure, the PT, is going to be partial pressure of A plus partial pressure of B. It means the pressure of A added with pressure of B, you will get the total pressure, which is 11 equals to 8 plus 3. So that individual pressure is called partial pressure. So how do we calculate that? Okay, in simple terms, it's like this. If I want to calculate the partial pressure of A, it's quite simple. 8 divided by total. What is the total? 8 plus 3 is 11. Then I times with total pressure. So it is actually 8 over 11. Total pressure in this case is 11. If I cancel, I get 8. That's the meaning. Okay, that's the meaning. So if I have partial pressure of B, it means I have 3 total, 11. So I times with total pressure 11. When I cancel, I get 3. This is the simplified version. Yeah, simplified version of this partial pressure. So let's see how do we apply. But before we apply, yeah, it's the same way. How do we deduce units? Okay, the units for partial pressure is Pascal. Okay, so if I have, like, for example, I want to find out what is going to be the unit of this A. Okay, quite simple. Okay, we know that partial Kp of this is going to be partial pressure of Cl2 times partial pressure of PCl3 divided by partial pressure of PCl5. And I know this is Pascal to the power of 2, Pascal to the power of 1, cancel, cancel, I get Pascal. So that is going to be my answer. How about C then? Okay, do remember this is, we are applying Kp for gas only. So you use for this and you use for this. Ignore this, ignore this. Okay, so when I write down, it's going to be partial pressure of hydrogen to the power of 4 divided by partial pressure of water to the power of 4. So this is going to be Pascal to the power of 4 divided by Pascal to the power of 4. Cancel, cancel, no units. Okay, that's the reason why they don't have any unit over there. Yeah. So you have some example over here, very, very simple. Okay, by using the partial pressure, you can calculate the Kp. Okay, but let's try some this example. This is also quite simple. Okay, I'll just show you over here. They say that, okay, you have this equation. The pressure exerted by this mixture of hydrogen, nitrogen, and ammonia, it means all three. So this one is what we call as total pressure. Total pressure is going to be 2 times 10 to the power of 7. Under this condition, partial pressure, they say partial pressure of nitrogen, okay, is going to be 1.490 times 10 to the power 7. And they say partial pressure of hydrogen is going to be 0.4 times 10 to the power 7. They already give you this. Okay, and then they ask you to calculate the value of Kp. In order to calculate that, yeah, you need to find out what is the partial pressure of ammonia then. Okay, because you already know the total pressure. So it's going to be quite simple. 2 times 10 to the power of 7 minus 1.490 times 10 to the power of 7. Okay, you minus with 0.4 times 10 to the power of 7. If you do that, okay, you will get this one is going to be 1.89 times 10 to the power of 7, 2 times 10 to the power of 7. So if this one, I think is 0.11 times 10 to the power of 7 Pascal. Okay, you will get this. That is going to be the partial pressure. Okay, and then you want to calculate Kp. Yeah, of course, you use the Kp. Kp is going to be partial pressure of ammonia, okay, to the power of 2, partial pressure of nitrogen, okay, times partial pressure to the power of 3 of hydrogen. So you just need to use all this value for ammonia. Okay, 0.11 times 10 to the power of 7 to the power of 2 divided by nitrogen is going to be 1.490 times 10 to the power of 7. Okay, and then this one is going to be for hydrogen is going to be 0.4 times 10 to the power of 7 to the power of 3. Okay, to save time, I'll just let you to calculate. Okay, if you calculate, okay, straight away, I think someone calculated already. Yeah, you will get all this information. Yeah, it's there. Okay, and then the unit also, you see the unit, this is going to be Pascal to the power of 2, then Pascal to the power of 4. It's going to be Pascal to the power of negative 2 if you cancel. Yeah, so you will get this as the unit. Okay, you can just, okay, very easy. Yeah, now if you look at this checkpoint number 9, okay, because some of the question will be, they will relate with contact process, they will relate with Haber process. So if they relate to that, how to answer? Okay, you see like something like this. You should know Haber process is going to be 450 degrees Celsius. Okay, and then they use this pressure and so on. Okay, so if you look over here, we know Haber process is going to be exothermic. They say that suggest why temperature more than 450 is not used. Okay, even though the rate is faster. Okay, so let's test and see. Okay, this is going to be negative. So if I put my hand over here, this is hot. Okay, this is cold. When I increase temperature, I need to decrease the temperature. How do I decrease the temperature? I will move to the left. Okay, you can clearly see here the yield. Okay, the yield of ammonia will become lesser if you use more temperature more than 450. Okay, that is going to be the answer that you will find it over here. Next question, suggest why the reaction is carried out at high pressure. Why they are doing it at a high pressure? Let's see. Okay, so all of them are gas. So this is 4, this is 2. High pressure, it means I need to bring the pressure down. How do I bring the pressure down? By favoring the less number of molecules. So you move to the right. So you are forming more ammonia. So of course you want more yield of ammonia. That's why you are doing that by increasing the pressure. Okay, you can read. And then they say, explain why removal of ammonia as soon as it's formed is important part in this industrial process. Of course, you need to remove it. If you don't remove it, you are not actually doing this Haber process properly, because the moment you remove it, okay, you are decreasing the concentration of ammonia. When you decrease the concentration of ammonia, you are trying to form more ammonia. Yeah, so it will, removal of this ammonia will shift the position of the equilibrium towards to the right to continue reacting to give you more ammonia. Okay, that is the explanation over there. And then when the ammonia has been removed, why doesn't it decompose back to hydrogen and nitrogen? To answer this, you write down the equation, ammonia. Okay, if I rewrite this equation in this way, I know that earlier it was exothermic, but now it's going to be endothermic. If I rewrite it like this, it means I'm taking the ammonia and I'm putting it somewhere. So what happens over here is, okay, you are not, okay, you do not want the ammonia to decompose. One, you do not have the catalyst, so don't worry about it. Okay, but under what condition do you keep that ammonia? Okay, you need to be very certain at it. Okay, because I don't want them to decompose. I don't want them to move this way. I want them to move the position to move this way. Okay, it means to reduce the decomposition. So what I need to do in order to move that way, you see, this is plus. If I put my hand, this is cold, this is hot. What causes the movement from cold to become hot? It means when I decrease the temperature, what I need to do, okay, I need to increase the temperature back, then I will try to make it to the left. Yeah, so it means I must keep this ammonia at lower temperature, and this will prevent decomposition. Yeah, that is the explanation, that is the answer for that. Okay, you see, there's no catalyst. Okay, but they are stored at very low temperature also. So therefore, ammonia, they don't decompose. Okay, this is another thing that you need to take note for this question. And the last one, okay, which can be done very fast also. Yeah, thank you for Christopher just now. I think you guys are answering and so on. Yeah, thanks. Okay, so here, okay, if you look at this Bronsted-Lowry theory, okay, according to Bronsted-Lowry theory, okay, acid is a proton donor, base is a proton acceptor. Okay, this is the only theory in your syllabus. Don't bother about Levy's theory. Don't bother about the other kind of a theory that is mentioned in different books. This is only the theory that you need to remember. Bronsted-Lowry acid is going to be proton donor. So if you look over here, HCl, okay, and then H2O, you see H2O changing into H3O plus. It means that H plus is given to this H2O. So this is a proton donor. This is acid. This is proton acceptor. This is base. Okay, simple as that. Okay, acid and base. In certain situation, you have a reversible reaction. Yeah, like for example, ammonia. Ammonia is a weak base. So when you write the equation, okay, you see this is going to be completely dissociating. Yeah, to give you a hydroxonia ion. But ammonia, when they react, because they are weak base, they must have reversible reaction. And if you look over here, NH4, it means that they are receiving H plus from water. So this is acid. This is going to be base according to the theory. Okay, according to the theory, they will behave as. Yeah, but do remember this is a reversible reaction. When this reaction is moving that way, that is base and that is acid. How about the reaction that is moving this way? It means that this NH4 will donate the H plus to OH to form H2O. So this will behave as an acid. This is going to behave as a base. But I will get confused if I just say acid, acid, and base and base. So what they did, they put this term conjugate acid, conjugate base. In the end, what happened? Base can be is actually conjugate acid. Acid is going to be conjugate base. Okay, that is the thing that you need to remember. So if you look over here, identify acid and base on the right hand. Yeah. So on the right hand, you see which one is going to be acid and base. Only one H, and then there is H is gone. Yeah. So here, what happened? They are receiving the H from here. Okay. So this is going to be acid. This is going to be base receiving. Okay. And here you see here HS, there is extra H over there. So they are receiving from here. So therefore, this is acid, this is base. And because they are on the right hand side, all of these are conjugate. Okay, you just put conjugate, 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 conjugate. Okay, and identify the same thing here, which one is going to be, which one is conjugate and so on. If I want to just write down, you see that this one receiving the H from here. So therefore, this is going to be acid. This is going to be base. And because of this, okay, this one you see, they are going to donate the H plus over there to form the water. So this is conjugate acid and this is conjugate base. And you can see they are partners. Okay, they are partners. Okay, so that is very important. Okay, and the last part is, okay, what are strong acid? Okay, it's something that is completely dissociate. Yeah, completely dissociate. So generally HCl, that's why HCl, we write H plus and Cl minus. If you have HCl plus water, we always write down H3O plus and then Cl minus. You see, they are straight line. Yeah, no reversible equation line. And if you have this weak acid, okay, you see all this, anything related to weak acid, okay, if I have CH3COOH, okay, I have to represent them using this way, okay. I cannot just simply represent them using a straight line, only one arrow over there. If I'm going to use water, okay, same, okay, I need to represent using this CH3COO minus plus H3O plus, okay, that one is important. The same applies to strong base and weak base. Just now, okay, I think yesterday we learned not only group 1 metal hydroxide is strong base, group 2 metal hydroxide also are strong bases also. Yeah, we have already learned. And then you can see weak bases, okay, for example, ammonia. Okay, that's why just now when we write the ammonia plus water, okay, we write it down as NH4 plus and then OH minus. And this one is going to be because ammonia is a weak base. Okay, that is the reason. And of course, there are some partial questions over here. Okay, maybe I just go through only one here. This is going to be negative, hot. Okay, this is cold. Okay, so what happens if you increase the pressure? So this one is 3, 2. Increase the pressure, you need to decrease the pressure. So it will move to the right. So of course, this is correct. Increasing temperature lowers the value of Kp. Okay, when you increase the temperature, you need to decrease the temperature. You move to the left. So Kp is going to be reactant product divided by reactant. Reactant is more. So Kp is going to be lowered. So correct. Presence of vanadium pentaoxide catalyst increases the equilibrium yield. No, they do not increase yield. They only increase the rate. So you will get this 1 and 2 as the answer. Okay, and then even this one, what will happen when temperature is changed to 600? Okay, normally it's 450. It means you are using higher temperature. Higher temperature, it will be faster, not slower. Okay, and then what will happen to the equilibrium yield? Then you put the hand. Okay, this is going to be hot. This is cold. So if you have higher temperature, you need to bring down the temperature. How do you bring down the temperature? By moving to the left. So equilibrium yield is going to be decreased. That's why the answer is A. Okay. And then here, okay, what is the partial pressure of this? You can do it on your own. Okay, this one also, I think the effect of increasing pressure, what happens? So you see 2 and then 2, nothing, no change, no change. Okay, and then if you increase temperature, what happens? This is cold, this is hot. Okay, increase temperature, you decrease the temperature. How do you decrease the temperature? You move to the right. Okay, move to the right, and you can see you can get it done very fast. Yeah, so I've done everything, okay, with you. Sorry for extra 3 minutes. Okay, that's all from me.